So this is the webinar that in which we are going to talk about the basic theoretical aspects of contact in the finite element method. So all of us have if we have some experience in finite element method, we have different kind of we generally model different kind of problems in finite element analysis, in which we generally come across the kind of convergence issues, or we need to model some complex phenomena. All of this from simple to complex. The contacts are take a major part in any of the physics modeling. So the content that I'm going to discuss today is I'm showing right now on the screen. So we'll first discuss the basic concept of the contact. What is contact in the finite element analysis, and how it is related to the physics that we are currently living in. Then we will see the types of contact in Ansys, or the type of contacts in general finite elements packages, like what kind of physics is simulated with the help of what kind of contact. Then we will see the basic kind of nonlinearities that are present in the finite element analysis, and we'll see how that contact nonlinearity come into picture in that FEA equation. So we'll see the equilibrium equation of the finite element method. Then once we have formed the finite element method equation, we will see how the nonlinear FEA solutions are derived. So the equations will be a nonlinear because of the contact nonlinearity, and how the equation is kind of solved, how the nonlinear FEA equation is solved, we will see next. Then we will see contact forces. So we have got the contact defined, and we have defined the equation, we have solved the equation. But in that equation, how to solve for the contacts, how the contact forces are solved, how the contact formulation is done, what are the ways, what are the formulations that are required to solve the contact problems, those things we will discuss. And then one or two advanced topics I have included as stiffness, normal stiffness, contact stiffness, and general convergence issues. Once the contact is solved, what are when we are solving the contact, what are the different convergence issues we are getting while solving the contact? Those things we will discuss in today's seminar. So this is like a brief introduction to the theory, and we are going to discuss what happens in the background of the software when we are solving the contact problem. We will see all types of contacts. So before going ahead with the types of contacts, I just wanted to tell you what is a contact in the simulation environment and the physical environment, right? So contact is a very trivial thing for all of us, like when we are walking on a road, when the car is rolling on the road, or just like Roger Federer, legendary tennis player, when the Roger Federer is playing on playing tennis, that time he has got a lot of contacts with the racket, with the court, everything, right? So if these are the trivial, we don't even realize that when we are talking on the road, there is a reaction that we are putting on the road, and there is a reaction that is getting acted, and that's why we are going ahead. Or when the car is rolling on the road, because of that reaction, because of that contact, frictional contact between the tire and the road, where the car is moving, car is moving, and that's kind of a trivial things we generally see in the outside world. Let's consider this example of Federer playing tennis. So this is a lot of contacts involved in this picture on the left picture. So he has a contact of his shoes with the court. Then he's holding the racket in his hand. So there is contact between the racket and his hand. Then he is going to hit the ball, right? When he's going to hit the ball, there is a contact between the wire mesh of the racket and the ball. So that kind of different physics that are getting involved on the left side image. So we will consider one contact out of it, the contact between the racket and the ball, right? So here, what happens when he's moving his hands and the racket touches the ball, he is going to exert some force with the help of that racket on the ball. So the force will be transferred from the wires of the racket to the ball, and the ball will change its direction. So if you look at this right side image, that is kind of modeled. So the ball will come and hit, it will deform the wired mesh, and then it changes the energy, or the force will be transferred from the racket to the ball, and then the ball changes its direction and goes to the other side of the other side of the code. So here, if you first thing you will observe is a force balance, or the forces are getting transferred in the contact. And the foremost thing is the contact should be detected. So in real life, the contact is bound to happen. When we are hitting the racket with the ball and wires are going to be in a contact. But in the simulation environment, it is different. Actually, if we don't define the contact between the ball and the racket, ball will simply pass through the racket or wire mesh. It is not going to, it is not going to naturally. The simulation doesn't understand there is a contact. These are two bodies are coming into the contact, and there should be some kind of physical interface between should be there. It doesn't understand it. It's basically a mathematical model we need to prepare in the simulation environment. So we need to explicitly define what kind of behavior is there. So here the ball will hit, there is a surface on the ball which will come into contact with the surface on the racket, and those two will transfer the energy, transfer the forces from one to other, and that's what the contact is defined in the simulation. So even though it's a trivial thing in the physics or the physical scenario, it is not that easy in the simulation environment. We need to define it a lot of factors, and those factors we'll understand what are the different factors and how that contact is being established in the with the help of subsequent slides. Sure. So we'll see the type of contacts in Ansys. These types are you can observe in other simulation softwares also, like Abacus and other softwares. So first is bonded contact. Bonded contact is kind of a contact where we have kind of two surfaces not sliding with respect to each other. For example, welding, brazing, or like tightly placed. If you have very tightly clamped two plates, that is where we can assume it is a bounded contact. So there is no sliding, no relative motion. The two faces are kind of stitched together. Then we have got the no separation contact, in which small frictionless sliding is allowed, but faces are not separating. The name itself suggests like there is no separation allowed. Then we have got the frictionless contact. Frictionless is the case in which two surfaces are sliding with respect to each other, and the separation is allowed, but the sliding is frictionless. So there is no friction, there is no kind of frictional force that is getting generated in the frictionless contact. For example, weld surfaces, you can see this kind of a frictionless contact. In the rough contact, it is similar to the frictionless contact, but very high value of mu, so it doesn't allow the sliding of the contacting surfaces. And if we look at the frictional contact, which is the very common in the physics, these are the kind of contacts in which we define the coefficient of friction value. We give the real values of the coefficient of friction, finite value of coefficient of friction. Then we model sliding, we model separation. Just like when Federer is running on the court, there is a frictional contact between his shoes and the ground or the court. So our car is running on the road. That kind of a contacts are frictional contact. So all those lot of contacts in the real life are frictional contact. But again, when an simulation engineer models any problem, he needs to go through that. If you are trying to model the actual physics, yeah, you can model it. You can model the frictional contact, but it comes with the computational cost, convergence issues. So just decide what kind of a contact you need to model. Like apart from frictional contact, other contacts are fairly easy to solve in the simulation environment, either in Ansys and Abacus. You can solve it without the convergence issues. And that's why it's an engineer's judgment to model it with the, do you think there is a relative sliding, it is happen, then model only with the frictional contact. Otherwise, you can go ahead with the other type of contacts also. Right. So we have discussed the type of contacts and what is the contact in terms of simulation environment. But how does it, when we go to the micro level, on the surface level of the component, how that contact is happening, how that physics of the contact is happening, that we will discuss in this slide, right? And where that nonlinearity is coming in the contact. So I have shown two bodies over here, body 1 and body 2. They have got the two surfaces. This is the surface on the body 1, and this is the surface which is not uniform on the body 1, and this is fairly uniform surface on the body 2. So these two bodies are moving towards each other. At some point of a time, they have initial gap. At some point of a time, they will come and come in contact, and body 1 and body 2 will exert pressure or the force on each other. So as we have seen, the racket will, when the Roger Federer hits the racket, he is going to transfer the force, whatever he is intended, from the racket to the ball. Similar way, the body 1 will exert force on the body 2, or if body 2 is exerting the force, it will transfer the force from body 2 to body 1. So when there is an initial gap present between these two bodies, this is the curve, like you can see on this side of this side of the curve, we have a gap. So as the bodies come closer, the gap like gap reduces and it becomes a zero. And when the bodies come in contact, those are trying to exert force on each other. So there is, you can see the contact force. This is the term contact force is getting exerted or is getting transferred from one body to other body. So that's what the contact force is getting generated. Here we have got the penetration. In the ideal contact, there shouldn't be any penetration, right? So if I'm walking on the road, or if the tennis racket is hitting the ball, there should not be any penetration of one body into the other. That's not possible physically. So there should be ideally no penetration in the contact modeling. And what happens and what leads to this kind of condition is that two bodies are coming together, two bodies are kind of coming towards each other, they are having a contact and they are exerting force on each other. So there was no force initially and there is a force when they are coming in contact. So there is an abrupt change in the condition that is happening, which is giving rise to kind of a different changes or different things we need to consider in the contact. So the bodies are incompressible, they are not penetrable, right? And they are going to slide with respect to each other. So what will happen? Let's assume this is the finite element technique we are solving, right? So we have got this different elements and nodes on this surface of the body. Also on this surface or this boundary of the body 1, we have got the different finite elements, and there are nodes all on these surfaces. So when the two bodies are coming towards each other, they are touching, the respective nodes on those bodies will come into contact and they will try to share these reactions and the forces. When they are sliding, again, the node 1 to node 1 connectivity will not be there. Node will touch on the node number X on the body 2. So that kind of a different scenarios are continuously coming when the bodies are coming in contact. And that leads to the kind of non-linearity in the contacts. I'm talking here only on the frictional contact right now. If we're talking about the bonded contact, there is no relative sliding, there is no non-linearity. But the main focus of today's lecture is mainly on the non-linearity and some part of the bonded contact. So there, that is where it all starts. Before proceeding into the equation of like where this non-linearity, where this sliding is accommodated, or how this sliding is solved in the actual finite element method or the actual finite element softwares, we will see the equation based on which the FEA formulations are, or the FEA softwares are based, right? So we have got this FEA formulation equation over here on the screen. The potential of virtual work, or the potential, like the equation of virtual work or the potential energy, is equal to strain energy minus the external work. This is the basic formula, or this is the basic equation of the virtual work. So we have got this potential energy or the virtual work is equal to strain energy, which is kind of produced with the help of stresses and strains in the body. We are talking only about the structural analysis over here, right? And there is external force which are creating the strain energy in the body. So those are minused from it. Like, so if you write an equation, P is equal to Ku minus F. K is the stiffness, U is my displacements, and F is my external work. Ideally, the virtual work should be 0 to get the correct exact value of the equation. So when we equate the virtual work or the potential energy to 0, we get an equation of Ku is equal to F. This equation you might have seen in your like finite element course. This is a general equation you might have solved the truss problems also, 1D truss problem or 1D beam problem, in which you have formed the K matrix of 1 by 1 or 2 by 2 or 3 by 3 like that, and you have got these displacements which are related to U, right, based on the external force applied. So This is the basic equation that we got from the principle of virtual work. Here we have U is the displacements. If you go to the problem of thermal analysis, we have got this U is replaced, like U is basically an independent variable which we need to calculate through this equation. We know the K, we know the external applied force, we can calculate the U. If the thermal problem is solved, U will be temperatures, which are trying to, like we are trying to find out through the simulation. For this today's scope, we will discuss only about the structure analysis and what happens and where this nonlinearities come into picture. So basically, there are three nonlinearities in the finite element method. First is a material nonlinearity, second is a geometric nonlinearity, and third is contact nonlinearity. Out of these three, the most difficult to solve the nonlinearity is the contact nonlinearity. Okay, so when we have the elastoplastic curve of the material that is inserted in the material properties, then this changes the stiffness matrix. The stiffness matrix is again consists of relations from the strain displacement as well as the material property. So the material properties are non-linear. That's why this K becomes non-linear. Then this whole equation becomes non-linear. Then when we are adding the geometric non-linearity, the strain displacement relations are non-linear. Like generally the strain is equal to change in the length divided by the original length. But if you look at the equilibrium equation itself, the Hooke's law and different terms of the Hooke's law, it says that there are like other terms if we include into the equation when our deformations are large, the deformations are no more linear, right? That time we include the geometric nonlinearity when the forces are not remaining constant, right? That time geometric nonlinearity is included in the K and it becomes a nonlinear. So where the contact nonlinearity goes on in the equation is the force. So we have got applied force from the body, and then there will be a contact force that will be generated in the body, right? So that force is continuously changing. So if you look at these two bodies, body 1 and body 2, when the bodies are like touching, let's say around 1 mm square or 5 mm square, the contact force transferred will be different when there is a lot of contact, lot of sliding happening. That is how the contact force changes. And when the force changes, the equation becomes a nonlinear. So we have got these nonlinear equations and we need to solve them, right? So it's not just the matrix inversion we are going to get, and we are going to get that U values just by matrix just by matrix inversion. So what we need to do, we need to have different solution techniques, different methods to solve those nonlinear equations. You might have studied in your numerical methods, the Runge-Kutta method, Newton-Raphson method. So different methods are there which are used to solve the nonlinear set of equations in finite element method. I'll just mention the name which is used by the commercial softwares right now in the industry. I'm talking here only about the implicit analysis. We are not talking anything about the explicit analysis. Implicit analysis methods, the solver is Newton-Raphson method. Newton-Raphson technique is used because it has got the quadratic convergence rate. So iteration by iteration, like convergence is achieved in like less number of iterations. That's what the quadratic convergence rate means. You can go on Google and you can search on that, like how what is the convergence rate of different numerical methods. So this Newton-Raphson method or NR method has quadratic convergence rate, which helps to get the convergence easily or with the like few less iterations as compared to other methods. So what happens, like I'll just this is a nonlinear curve you can see in the black. I want to go from point G to point A. So what we'll do, like this is the blue line you can see is the initial stiffness of the system. It's a linear stiffness. So I want to go from G to E. So I'll draw an line. Then I will go to point D and try to achieve the point E. Then I will again calculate the tangent stiffness matrix or the stiffness matrix, that K, right? K. So I'll again calculate it based on the current system. Then I will calculate the stiffness. Then I will calculate the norm, like linear stiffness. This is a 1 point, right? We have got the one value of a stiffness. Then again I will draw a tangent line. I will go to point B and I will try to get the point C. Then again from point C, I have to go to the point A. So this is how we are trying to like piecewise, small pieces we are solving of the complete problem. If it's a linear problem, I have to go from point G to some point X over here. We have to just, it's a line equation. You can get the solution with the help of line equation also. So in reality, if you look at the problems you might have solved in the linear finite element analysis, you can, whatever results you get, if you 10 Newton is applied and if you are getting 2 mm of a deformation, for 20 Newton it will be 4 mm deformation. It's that it's a linear nature, but it's when the contact nonlinearity is present, or any other kind of a nonlinearity, material or geometric, we observe some kind of a trend in which in geometric nonlinearity we don't observe that much change in the deformation, but in the material and contact nonlinearity we are certainly bound to get a major difference in the performance of the structure. Yeah, so where it has to follow piecewise different sections of the curve, and it solves for that small sections, and those are called as iterations in the sub, or those are kind of iterations that the solver takes while solving the finite element problem. As you go on reducing that size, it will be more easy for the solver, but it will be time consuming for the user, that it takes a lot of time to solve each, and it forms the tangent stiffness matrix at each point, then it again solves for the independent variable. It goes on like that. So it's based on the user and its user's experience, like how to proceed with the defined number of inter iterations or the substeps. So this is how the equation of the nonlinear equation of the finite element method is solved when it has got a nonlinearities, right? So now what we'll do is we will try to formulate the nonlinear equation with respect to the contact nonlinearity, right? So we'll not include, this lecture is about the contact nonlinearity. So the kind of equation I'm showing right now on the screen is including the contact forces in the normal direction and the contact forces in the tangential direction. So if you remember, we have got this equation of virtual work is equal to strain energy minus the forces. So I have included here the contact forces in the normal and the contact forces in the tangential direction. This is the strain energy, stress into strain over the volume V. It is giving me the strain energy. And the integration of this, the contact properties and the force or the contact function, right? Contact function, when the two bodies are coming in contact, how that forces are changing, that contact function, those in the normal direction and the tangential direction, those will give rise to the contact force on the normal and tangential direction. What does it mean by tangential direction, normal direction? I'll just briefly tell you. When the body is sliding, one body is sliding on the other body, it is, the first thing is it should not penetrate, the two bodies should not penetrate within each other. And the other thing is, when the sliding is there, it should not be a kind of a frictionless sliding. There should be some sliding, there should be a sliding with some frictional value. So it gives rise to the tangential forces. If you remember, in academic, we have a block sliding on the floor. That time we have defined there is a force, contact force, opposite to the motion of the block. So that is a tangential force, or the tangential force in the contact. So these two contact forces needs to be calculated in the simulation, and these two contact conditions needs to be satisfied during the solution.